Hi, today we're going to do a cloud chamber. I'm going to go through the principles, the design, engineering, construction, and operation of this cloud chamber. And then we're going to go ahead and we're going to mess around with some subatomic particles. Are you ready? So cloud chambers have been around for over 100 years, and they were one of the first devices used by physicists to be able to detect and study the properties of subatomic particles. Modern atomic force microscopes and scanning tunneling microscopes are actually able to visualize individual atoms. But even the largest subatomic particles are thousands of times smaller than that. You can't see them directly, but you can detect them and you can study them using a cloud chamber. And the way that works is a cloud chamber creates a layer of supersaturated alcohol vapor that allows you to visualize them because it's a metastable layer. Metastable means stable, but like a house of cards is stable. Even the tiniest little perturbation will cause the whole house of cards to crash down, greatly amplifying the initial impulse and causing the vapor to condense into a tiny little droplet. And millions of these droplets will track out the flight path of these subatomic particles and allow you to see them. The way you create that supersaturated layer is at the top of the chamber, you produce a layer of warm alcohol vapor. You could use any kind of an alcohol. You could use methanol, ethanol, isopropyl. I'd stay away from methanol because it has almost no aroma and it's toxic, so you don't know if you're being surrounded by a large quantity of that alcohol vapor. Ethanol is a reasonable choice, and heck, you can even make it yourself. But for convenience purposes, you probably want to use isopropyl alcohol. And the alcohol itself, because it has to be warmed and because it has to be put at the top of the container, what we do is we put a heat source in the containers with the alcohol and allow them to warm the alcohol vapor up. It then forms a layer at the top of the container, and as that warmed vapor begins to settle down, it becomes denser. It continues to become denser and denser until it reaches 100% saturation. At that point, you would think it would begin to condense, but it doesn't. It continues to get denser because there's a little bit of an energy barrier that has to be crossed to get those individual alcohol molecules to get together and form a liquid. It's sort of like the two molecules are looking at each other out either side of the room and going, go ahead. And the other one's going like, no, you first. And until they get dense enough, very close to the bottom of the tank, they won't spontaneously condense. And it is that supersaturated layer that forms that allows us to have that metastable environment that will track the contrails of the subatomic particles. So we need to warm up here and we need to cool down here. First question you'll probably ask is, how big should I build it? And this is one of the situations where size does matter, because some of the events that you're going to want to look at are going to be relatively rare. And if you have a very small volume of material, you might not detect it or have to wait a long time to be able to see the event. In addition, some of the interaction paths of these subatomic particles take a fair distance to occur. So in order to capture the entire interaction, you need a large container. So the bigger, the better, within the limits of your budget and what you can move around and you can store. Height is also important because the taller the chamber is, the thicker the level of the supersaturated layer is, and again, more volume for detection. Now, when you look at this, you might say, this looks a lot like a fish tank. And some people have actually used fish tanks for this purpose. I wouldn't recommend doing that for a couple of reasons. A fish tank has to be built rigidly enough to withstand the hydrostatic pressures of the water inside. And so if it's built out of glass, typically you will have a joint that is an epoxied joint. Or if you're going to be using acrylic, like we've done here, you're going to end up using a solvent adhesive usually based on methyl ethyl ketone, or MEK. And that adhesive acts by dissolving the surface layer of the acrylic panels right at the joint. When that liquid flows between the two joints, it produces a weld. And as soon as the as soon as the MEK has evaporated, you have literally an acrylic to acrylic bond. It's super strong, it's very clean, it's easy to do, and I've done this for a number of fish tanks. It's effective. But in both cases, those joints are rigid. And because we're going to be producing a temperature differential across this tank of over 100 degrees Celsius, there's going to be a lot of contraction and expansion of these panels and a lot of stress. A better way to glue up these joints is to use a 1-part RTV silicone adhesive. When this stuff cures, it's still able to stretch almost 1,000%. It's rubbery, and it will allow you to take up some of that expansion and contraction movement at the joint rather than just stressing the panel. It's a better way to do this, and it's still quite strong. You can move this thing around. Now, when you're building the rectangular structure like this, a real neat trick to use are these sorts of things. They're corner clamps. You're probably familiar with these because you use them to build picture framing or architectural molding. They will hold the panels at a nearly perfect right angle and actually allow you to apply pressure against the panels to get a good approximation. And if you were going to be doing this entire rectangular wall in one step, you would need 8 of these clamps. But they're inexpensive, they're very easily available online or even at big box stores. And there's a saying in boat building that is, you can't be too rich, too thin, or have too many clamps. So this might be an excuse for you to pick up a couple of these. Now, once you've built the rectangular structure, the other problem with a fish tank is the bottoms tend to be made out of glass or plastic, and that's a bad thermal conductor, and we need to cool the bottom of the tank. A better way to do this is a metal plate or a sheet, copper or aluminum. I'd recommend the aluminum because, first of all, it's cheaper, it's lighter, and you can get it from the manufacturer already with an anodized coating on one surface. The anodized coating gives you a black, non-reflective surface and gives you much better contrast when you're looking at the contrails or at the tracks of the subatomic particles. The anodization layer is much more robust than paint, and it saves a step. To apply it, you would simply cut that panel to the outside dimensions of your tank, put a little bead of the RTV along the edge, put the panel down with the black side in, and then put a load spreader like a board across this and a little weight. And overnight this will cure, and you've now got an upside down version of a fish tank or a cloud chamber. The final panel is the top, and it is critical because you need to keep the inside pristine, absolutely no dust and no thermal motion, no air currents inside, because you have to get stratified layers. To do this, it's simply a cut of a piece of acrylic, the same dimensions as the outside of the tank. And then what you do is you apply, let's see if I can turn this over, a thin, very compliant, very soft weather stripping with a self-adhesive layer that allows you, when you put this down, to seal the tank simply with gravity. And now you have a nearly airtight container. The base of the structure is constructed from the same stuff that I use for a lot of my projects. This is a rigid PVC foam board. You can get these at big box stores, hardware stores. It's really nice for a number of reasons. First of all, you can work it using woodworking tools. It's relatively lightweight and stiff. It glues well, it holds screws well. It's a great thermal insulator, electrical insulator, it's waterproof, and it looks pretty nice. So that's what I built the outside from. However, we need more insulation because of what we're going to be putting in here. And so I took a 2-inch thick piece or 5-centimeter thick piece of rigid polyurethane foam, cut it to fit the inside of the box, and press fit it all the way down to the bottom to provide a nice thick insulation layer. I took a second piece and again trimmed it to fit the inside, then set the tank on top of that, drew a pencil line around the outside, and then using a razor blade cut out this square like this that just fits the outside dimensions of the tank. Now what you see inside the tank are a series of 7 of these 1.5 millimeter or 1/16 inch aluminum L pieces. And what they do is really useful, and I would highly recommend using this, is by sitting in the bottom of the tank, in the bottom of the container here, they provide support so that when the tank goes in, it will sit about 1 centimeter or a little bit less below the upper level of the polyurethane. And it will be supported there all the time at that level. But the other reason for these is that when you're going to be using a cryogen to cool this off, either dry ice or liquid nitrogen, as it evaporates or sublimates, it's going to be moving away from the bottom of your tank. But because the flat part of these is always sitting underneath the cryogen, it allows you to spread the cold, and it transfers it up to the blades that are in metal-to-metal contact with the bottom of your tank, providing really good thermal contact and transfer. This really works nicely. So now let's go ahead, and I'm going to load this up with about 5 to 6 pounds or about 2.5 kilograms of some dry ice. And you can tell the amount doesn't have to be that accurate. I'll give it one more. This quantity of dry ice, when this whole thing is set up, is enough to last about 12 hours. So plenty for a project or a school demonstration or to show your friends and family. Lift this guy up and settle it down like this. And sometimes it takes a little wiggling if I've got a few rice grains on there. That should work okay. Okay. Good. Now what I'm going to do is I'm going to use some of this EDPM closed cell foam rubber. And we're going to feed the power lines from the heaters inside of here and stretch this around like this. And then we have to press fit this all the way around the edge. You want a reasonably tight fit, so you have to do a little bit of work to get this to settle down. It's not bad. But what this does is it provides a black surface, which again improves the contrast when we're going to be visualizing the contrails. But it also helps to seal this up a little bit better thermally, giving a little bit more longevity to the dry ice or whatever we're putting in there to cool this. Now the next thing that we have to talk about is the lighting. It's key, because even if I do everything right at this point, if we just illuminate this with the ambient light in the room, we'll never see anything. We need very intense tangential light to reflect off the droplets to really see what's going on. What we want is sort of a slab or a layer of light that fills the supersaturated layer and nothing else. That would be optimal. To do that, I built these. Now these lights are constructed with a heat sink, and on the front surface of the heat sink, inside of the box, you can see that we have 7 Cree 3 watt, nominally 3 volt LEDs that have been thermal epoxy glued to the front surface of that heat sink. And then they have been wired up in series, so that when we drive this with about 21 volts, we'll get about 21 watts of light out of them. Now, I don't need nearly that much light, but the reason for making this so broad, using so many of these, is so that the light is generated by a large width, so that we're not having a cone effect, we have more of a slab effect or a wedge effect as we're moving across the tank. Now, these LEDs come in a variety of different colors and power levels. We get these from Rapid LED. These Crees are probably about the best I've ever worked with. They're really nice lights. And they come in red, blue, green, white. But of course, because we're dealing with radioactivity, I had to pick green. Now, another problem with these lights, or an issue with these lights, is their large natural divergence. It's about 135 degrees. huge wedge or divergence angle. And we don't want that because we would end up flooding the entire tank with this expanding cone of light. So that's why we built this box that sits on top of the heatsink. And what that does is it causes only the light that is diverging slowly enough that it can get out through this small gap at the end here. And so when it comes out at this point, it doesn't diverge very quickly, which is what we want. The problem with that method of spatial filtering is that we're going to waste about 90% of the light as it's absorbed by the super black paint that we have on the inside of this box. So what we did is we went to a company called LED Supply, and we bought some of these molded acrylic lenses. These things cost about $1.30 or so a piece, and they have 4 little legs on the bottom and a little lens on the top surface. So when you mount them on top of the LED with the legs down, you take a couple of drops with a toothpick of a UV curing adhesive, put those drops at the contact point of the legs, take a UV flashlight for about 5 seconds, and you permanently mounted the lens on the front surface of the LED. This will draw down the divergence to about 20 degrees instead of 135. That's still not narrow enough to make it completely out the end of the box, but it means that the vast majority of the light will make it out of the end, so it makes it more efficient. As a consequence, when this thing is running at full power, you can barely detect that the heatsink is getting warm. We're not pushing anything near its limits. It works really, really well. Now the light itself has to be mounted on the side of the box to produce a horizontal path of light. And so we took the box and we placed a couple of gussets on the bottom surface to rest against the sides of this box, and then drilled a couple of holes appropriately spaced so that this thing would be held the right distance from the side of the tank. And if I put this in here like this, we then use those pre-drilled holes to transfer the holes into the side of the box. And then with those holes, we tapped them so that they would take a thread. And then we took a threaded knob like this, and it goes through this and into the hole like that. And on this side, like this. And when we screw these things all the way down, we have a nice rigid connection. Another little shop trick, or a little thing that you might want to be aware of, is these knobs that we're using. We buy them from McMaster Carr, and they're sort of you-do-it-yourself knobs. They're based on a socket head cap screw like this. And they can be press fit into a variety of different size, styles, and color knobs. And because you're making them yourself, you can make them whatever length you want. You can use whatever type of screw size you want. They make them in metric, they make them in imperial. And so you can make up a knob that just fits your project just perfectly, and it makes things look kind of nice and kind of finished, and they're not expensive. So I'm going to finish screwing these things down, and then I'm going to put the identical light on the other side of the box, and we're going to get this thing running, and you'll see what the light looks like. So now I'm going to go ahead and turn this on. Let's see, start a little low just so we don't overdo it. And we'll get this up to around 21 volts, and then you'll start to see the green light. Like that. All right, so let's go ahead and add the alcohol. I'm going to fill it up about halfway. Same thing here. Then we're going to add some alcohol to the bottom of the tank. We're going to form a layer on the bottom. And the reason for this has nothing to do with the alcohol itself, it's optics. Because you can see these little droplets that form on the bottom of the tank will produce sort of a snowfield effect, kind of a refractive sparkle. And they'll make it harder for you to see the particle or the contrails than a flat piece or a flat layer of black liquid. So you only need enough just to wet the entire bottom. It doesn't have to be a certain quantity. And the less is better because you're not wasting any material. All right. We'll go ahead and we're going to close this up like this. Keep it as clean as we can. Clean is important. Now, while this is cooling off, what we're going to do is we're going to talk a little bit about the method that you use for cooling. Obviously, I decided to use dry ice, but there are different options. If you're building a very small cloud chamber, which I wouldn't recommend, you might want to use something like one of these. Peltier devices, thermoelectric coolers. We've done a number of videos on these, and they're pretty interesting. You might want to take a look at them, what they can do. What makes them nice is that they're solid state, they're relatively inexpensive, they're compact, they're very rugged, and they're very easy to drive. Just a DC voltage from a battery, and they will produce a temperature differential across the surfaces. They're called thermoelectric coolers, but that's a bit of a misnomer. They are really thermoelectric temperature differential machines. One side gets hot, one side gets cold, relative to each other. So in order to get the cold side to be cold, you need the hot side to be as close to room temperature as possible. The hotter it gets, the less cold this side is because the temperature differential is always the same. So to get the highest amount of cooling, you want the hot side to be as cool as possible. Generally, that means you apply a heat sink and a fan to the hot side in order to get it to refrigerate. The problem with these things is they're quite inefficient, and you have to use several times as much power to drive them as they're actually able to flow through them in order to do cooling. So with a very small chamber, you might get away with it. But for something like this, you would have to tile this with a dozen or more of these devices, pump hundreds of watts of DC power in to get them working, put a bunch of heat sinks on the bottom and blowers in order to get rid of all that extra heat. It's probably not a good technique. A better method would be to use a phase change refrigeration system. You can buy these things where they have cold plates that you could apply to the bottom of the tank, but those things are quite expensive. If you get them made for that kind of purpose, they're going to cost many times more than your cloud chamber does. But if you're working, say, at a natural history museum and you want to be able to flip this on and off every single day and you don't want any consumables, that's probably a good choice. You could hack something out of say, a chest freezer and try to put something together yourself, but it's a lot of plumbing work and you're probably going to end up having to evacuate and recharge it with some Freon, so it's a lot of extra work. If you're going to use this thing one time a week or a few times a month, using a cryogen is probably a better choice. I decided to show you this with the dry ice, but this tank will also work with liquid nitrogen. Now you might think liquid nitrogen would be crazy. It's like, I'm not a university, we're not in a laboratory, that's an exotic material, it's dangerous. It really isn't, and it's something that you really might want to consider if you're ever going to do projects where you want low temperatures. Dry ice obviously is a solid, so you can contain it in containers that don't require a liquid tight holding container. But dry ice also doesn't have the ability to flow into little channels and tubes. Liquid nitrogen gives you that ability. In addition, liquid nitrogen is much colder. You can go 100 degrees colder. If you want low temperatures, you can pump it 100 degrees Celsius colder with liquid nitrogen. The other thing about liquid nitrogen and dry ice is they're quite safe. Both are non-toxic. Nitrogen is 80% of what we're breathing right now. And so if I were to take 20 or 30 liters of liquid nitrogen and I were to pour it onto the floor in this room and shut all the doors, the increase in nitrogen concentration in the air would be a couple of percent and therefore decrease in oxygen concentration. It would be equivalent to me going about 500 to 1,000 meters higher in altitude. I wouldn't even be able to detect it. Same thing with CO2. If we took that entire container I have of dry ice and poured it onto the floor, most of the CO2 is going to stay on the floor. And at low levels, carbon dioxide actually is a respiratory stimulant. You have chemoreceptors inside of your body that detect carbon dioxide levels and drive your respiratory rate. So at low levels, you're actually going to be breathing deeper. And to get to levels where dry ice or carbon dioxide is actually an anesthetic and can knock you out and essentially kill you, would require many times this container's worth of CO2, and you'd have to lay down on the floor to get there. They're quite safe. The significant difference between the dry ice and the liquid nitrogen is cost. Dry ice is actually about 2.5 times as expensive as liquid nitrogen. Here in New England, $1's worth of dry ice will provide about 200,000 joules or watt-seconds of refrigeration capacity. Liquid nitrogen, that same dollar will buy you about 520,000 joules of refrigeration capacity, so it's cheaper. The final difference between the two is how you're going to contain it. If you have, I'll bring this thing over here so you can see it, a typical cooler like this, for picnics. You probably have one of these lying around. You bring it to a food storage or transport area or a welding shop. They can load it up with dry ice. You go ahead and use it, and the next day you can put beer and hot dogs in it. So you probably have the ability to do that. But this kind of a container will actually only retain the carbon dioxide before it completely evaporates out for about 2.5 days. And even this mega container that I use, that you can't buy, this container itself, I had to build this with the huge thick walls, will only retain the dry ice for about a week. So something to think about. Liquid nitrogen, on the other hand, you have to invest some money. If you get a container of liquid nitrogen that is about the size of the pot on our still, it will hold about 20 or 30 liters of dry ice. And you can pick one of those up on eBay for about $200 or $300. Or if you want a lot of liquid nitrogen, you can go to your welding supply house and they can provide you with a tank like this. They'll lease you the tank for about $20 a month, and they will actually deliver it to you for $20. So kind of nice. The main difference, though, is the liquid nitrogen in those containers will last about a month. So I'm not saying that liquid nitrogen is superior or inferior to dry ice, but consider it and don't just discount it out of the gate if you're going to be doing any kind of low temperature experiments. So now if you look inside of the container, you can see these tiny little droplets. It almost looks like it's raining or snowing inside. And that's the condensation of the saturated layer of alcohol vapor as it's dropping down toward the bottom. But because of residual turbulence in there, maybe even a tiny bit of dust that's in there, we don't have any kind of layer of supersaturation. Those droplets are beginning to form at the saturation level. So we don't have that metastable environment to be able to detect any kind of trails. We've only been waiting about 5 minutes. Give it another 5 or 6 minutes, things will continue to stabilize, and then we're going to be able to detect the contrails. So now what I'm going to do is I'm going to load, while we're waiting for this to stabilize, I'm going to load one of the first radioactive sources. And what that's going to be is a thorium-doped tungsten inert gas, or TIG, welding rod. Typically, rare earths and thorium were added in just about 1% or 2% concentration to these welding rods to help stabilize the arc and improve the welding characteristics. But nowadays, in the last couple of decades, it has become less and less popular to use thorium because it has a low-grade radioactivity to it. And it's such a low grade of radioactivity that it can't actually penetrate the dermis of your skin. It doesn't even travel very far from the surface through air. But if you are going to cut these rods or you're going to grind them for a welding operation, you produce dust. And if that dust gets into your lungs don't have that protection, and it can cause cancer. And that's why they've fallen out of favor. But they're a great source of radioactivity. The thorium has a half-life about the age of the universe, so it's never going to run out on you. And once this stabilizes, we'll be able to start to see some of the contrails formed by the alpha and the beta emissions that are given off by the thorium. Now, just to demonstrate that these are in fact radioactive, I'm going to put on some gloves here. Gotta maybe back off on some of that growth hormone. And we'll turn on our radiation detector. And I'm going to hold this near the thorium rod, and you'll see what I mean. Not much at even this kind of distance. But as I move it closer, you can see that it gives off a decent amount of radioactivity. So now we have to begin the weighting process. Like I said, it takes a little bit of time for this material to stabilize to the point that you're going to be able to see the contrails. So we're just going to have to wait. Now it's been about 5 more minutes since you saw the original image from the side, and you can see all the contrails that are formed by the different particles coming from the thorium. Thorium generates alpha and beta particles. Alpha particles are helium nuclei, 2 protons, 2 neutrons, and positively charged. They're relatively massive and slow moving, and they tend to produce thick, short contrails because of their slow speed and their interaction with the medium around them. The very thin, fine lines that seem to go a lot farther are made out of beta particles. It's another word for electron, negatively charged electrons. They tend to move faster, and they tend to move a little bit farther through the medium before they interact with material, just simply because they're so small and they are moving quite quickly. But one of the things that you might notice, one of the key things, is that the particles don't seem to necessarily be coming directly from the source. Some of them do, but some of them also seem to be generated at right angles and tangential. The reason that is because when the particles leave the source, the thorium, what they do is they careen into another particle and they deflect off like billiard balls. And you may not see their original course, but you see the 2 particles that are moving in opposite directions once they hit those other particles. And so they'll seem to be coming out of nowhere and then disappear. And that's why you see sort of a hodgepodge of different types of angles and directions. In addition, because of the fact that we don't have any kind of electrical field here, these positive and negative particles are acting pretty much the same way relative to a neutral or a non-magnetic field. A lot of the early cloud chambers used powerful electromagnets to produce an electric field, and seeing the bending of these different pathways, they could determine the masses and the energies based on the radius of curvature of the different particles inside. Pretty neat. So now let's go ahead and replace the thorium with 2 other sources. All right, so now I'm going to replace the thorium with a different radioactive source. It's super cold in there, so I'm going to use the forceps to pick this up. Now the next radioactive source I'm going to put in there is lead-210. All of these radioactive sources come from a company called Spectrum Techniques. They sell radioactive sources for things like cloud chambers, and because they give you so little radioactive material, it's actually possible to get this shipped by standard ground transport, and that makes it very convenient. And what I like about that too is that they give you a variety already set up by placing the radioactive source in the eye of this little needle, and the cork just simply has the point of the needle in it, so it holds it up into that supersaturated layer. We'll put the lead over on the right side. And then the other material I'm going to use is strontium-90, and this produces a different type of radioactivity. I'll put the little washers around here. Don't poke my finger. Like that. And we'll put this thing in here over here. And we'll close up the top, and then once again, we got to wait because we have to get that stratification to occur. So we're going to be here for about 10 minutes. Just waiting. All right, so you can see the distinct difference between the 2 radioactive sources. The lead-210 actually produces both alpha and beta radiation. A lot of the alpha you can see radiating close and not moving very far from the source around the right hand or the little needle that I have my finger pointed at right now. That's the lead, that's the alpha emitter. That's the lead, that's the alpha and beta emitter. The strontium-90 is only a beta emitter, electrons. And so it doesn't have the fat types of contrails surrounding it, it's surrounded by the finer, thinner electrons that are interacting around it. There is a little bit of mixture that you can see between the two of them simply because of the fact that they're close enough that some of the particles are actually able to move over to the other, but our tank isn't big enough to completely isolate them. Now what we're going to do is we're going to kick things up a notch, and we're going to use a far more powerful radioactive source, polonium. I'm going to show you the significant difference between the two types of radiation level. The thorium rod that we had inside of here produces a decent count. About 600 counts per minute, and it kind of stabilizes. Okay, 700. But the polonium source over here is a little bit different. The radiation doesn't travel very far, but it's much more intense. Sort of pegs the meter. But not very far. This is an ionizing filter radiation source, and it ionizes the air in order to make it make particles like dust particles sticky. And the difference is that unlike a half-life of the life of the universe, this has a half-life of 138 days. So we've had this for about that period of time, and it's actually 1/2 the intensity it was when it was first produced. And after 1 year, it has 10% of the radioactivity that it did when it was first produced. So that's why these have to be replaced. So I'm going to go ahead and put in a little support to keep it all out of the alcohol, like that. And then I'm going to put the polonium source in here like this. And you want forceps when you're dealing with that kind of level. And we'll go ahead, put this on like that. And then, you guessed it, we're going to have to wait about 10 minutes or so. Now, polonium is only an alpha emitter. And as a result, it doesn't have a very long range of effect, which is good because that means that when you're putting these in ionization filtration systems, you're not going to be sending very long range radiation particles very far because they get blocked by the air. But nevertheless, they produce a fair amount of radioactivity, and you can see that most of the pattern of the contrails produced are thick and heavy. You'll rarely see, though, a couple of very thin, very long-range lines, and that's because the alpha particles, when they hit another particle, can ionize them and knock off an electron, and so you sometimes get that cascade effect of secondary and tertiary particles from the original alpha particle. Nevertheless, it's pretty impressive, and I wouldn't want to have somebody walking down the street with an umbrella poke some of that stuff into my leg. Not too cool. Finally, we're going to do one more source. We're going to kick this up one more notch, and I'm going to show you my favorite source. But to see that well, we're going to actually turn up the heat on the alcohol supply. We're going to increase the brightness of the light and give it even more time for a good stratification so that you can detect it. It's really pretty interesting. So as you can see, it's really beautiful. You can see the little patterns of the different particles as they're moving through. Can you see the source? Neither can I, because the container is empty right now. What's causing those contrails inside of the cloud chamber is cosmic rays. Cosmic rays are very high energy particles that originate from cataclysmic cosmic events, billions of light years from Earth. And they slam into the upper atmosphere and create secondary, tertiary, and quaternary showers of additional particles that continue on through the atmosphere, right through the roof of this building and into the cloud chamber. And that's what you're seeing inside of there. It's beautiful, but it's a little bit worrisome because those same cosmic rays are plowing through every square centimeter in this room. They're plowing through me, the camera, and unless you're sitting in a salt mine while you're watching this video, they're plowing through your body as well. And it might do a little bit to explain spontaneous mutations, cancers, evolution, and even the ghost in the machine, those little stray bits of code that are floating around that produce unusual results in very, very sensitive pieces of equipment. Kind of something to think about. So beautiful, but maybe a little troubling. In any case, I hope you found this interesting. If you have any questions, you have any comments, put them down in the comments section below the video because I read them all. I'll answer as many questions as I can, and sometimes you give me good ideas for future videos. And if you like the kind of material that we cover in this channel, please consider subscribing. I know every channel asks you to do that, but it's the one way that you can sort of throw coins into the guitar case of us street musicians. It helps to augment the algorithms that YouTube uses to distribute our videos, and it helps to give us a little bit more gravitas when we go to companies like Alteros or MIT or any other kind of a company to get tours and to get access to equipment. So it really helps us out and we really appreciate it. But in any case, I want to thank you very much for watching. Stay safe, don't worry too much, and you have a good evening. We'll see you soon.